Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. Today I wanted to go over diode analysis. So here I've summarized the method for analyzing diodes. For an ideal diode, all you're going to do is assume it's either on or off. So if it's on, then you're going to just replace it with a wire. And if it's off, you're going to replace it with an open. So this is the easiest model and it's the most ideal. So when it's off, you'll have an open. So this is the first method. The second method is to redraw the circuit with a new model that is a little bit more accurate. So the on and off is just making very crude assumptions and it's not taking into account anything that's really happening within the diode. So it's not a very accurate model, but it can help you get a ballpark figure, which you can then take to an analysis or simulation software package and be able to get an accurate answer. So if the models that you can actually replace it with is the ideal model we already went over. And then there's also a full diode equation. So this diode equation, typically when it's on, you use an approximation of this IS e raised to the VD over NVT, where IS is the saturation current. And the VD is your voltage across the diode. And N is a processing parameter. And VT is called the thermal voltage. And for thermal voltage, we typically use a room temperature thermal voltage, which is approximately 25 to 26 millivolts. So that would be the value you would get for the thermal voltage at room temperature. If it's anything else, so if you ever work with applications that are going into space or extreme environments, make sure you use a different value for your thermal voltage. So the diode equation is an exponential form and looks like this. For the simulators, this is usually the equation that they use, and they do an iterative process so that it will get to be a very, very accurate number. We don't want to do that by hand typically, so we're going to approximate this by a different model, and the one that's the easiest to analyze by hand is this constant voltage drop model. So what we're going to do is when it's on, instead of replacing it with a wire, we're going to replace it with just a voltage drop VDO. When it's off, we will still open it up like a wire. So this gives us a more accurate approximation where it just looks like a line approximation. So when it's on, it's at a fixed voltage on your VD, and then your current can pass through it. And we don't model the passing through it in an exponential form. We just say that it constantly goes through it once it's turned on. So this is the easiest one to do by hand. The other one that I just wanted you to be aware of is called this piecewise linear, and it replaces it when it's on with a voltage and another resistor. And so that just adds in a little bit more complexity to the hand analysis, and the constant voltage drop gives you still a good accurate ballpark pretty quickly. So we are going to use this constant voltage drop model for all of the analysis that we do. So the method is to assume it's on or off. Then we're going to redraw the circuit with the new model. In our case, we're going to use the constant voltage drop model. So replace it when it's on with a voltage source. When it's off, it will be still an open. And then we're going to solve it for your currents and your voltages within the circuit. And then we have to check and see if our assumptions were correct. If they were correct, the check is that if it's on, your current is greater than 0. And if it's off, the voltage across it you'll still find is less than or equal to 0. If it is correct, then you're done and you're like, okay, these are the answers. If it's not correct, your assumption was wrong, you have to iterate it and assume a different stage. Whether you assumed on, you'll assume off now, and then analyze the circuit again. So this technique where we take a nonlinear element such as the diode, we replace it with a model of elements that are easier for us to analyze, such as a voltage source in this case. We analyze the circuit for both currents and voltages, and then we check our assumptions to see if they are correct. And so this method is what we're going to use for every nonlinear element. The other thing we're going to do is look at DC and AC analysis. So for DC analysis, we have that model of the diode being replaced with just a voltage source. For the AC, it's a little bit different. So if we were to analyze a diode, the DC side would look like this, and then we would have to figure out what we would model it with in the AC. What happens in the AC is that it's going to be hard to analyze both the DC and the AC together. So what is found in the derivation is that we can use a parameter, and in this case it's called the small signal resistance, which is the derivative of that exponential. So when we take the derivative, we find the slope of a line, and it intersects the current equation, and that slope ends up being 1 over RD. And so this number can be calculated by the NVT over ID. So if we look back at this equation, we take the derivative of this, and we take the derivative, then the exponential, these numbers come down, and that's where the 1 over RD comes from, is that NVT over ID. So what we find is that if we solve our circuit first for DC, plug in these numbers from DC into our AC parameters, then reanalyze the circuit with the AC model, and then we can sum these up like superposition for the total amount. So DC analysis, use the DC analysis to find your parameter, in this case RD, analyze the AC, and then you're going to sum the total to get the DC plus the AC result. So this is just that summary, and now let's look at an example. So here we're given our parameters. The VD is 0.7, and the N is 2, and VT, which is that thermal voltage, is 25 millivolts. We're going to use the constant voltage drop method, and we're going to reanalyze this circuit. So we want to find all the currents going through the diodes and the voltage V0, which is located in the middle. So to make an assumption of which way they're on or off, you're going to first look at the voltages without assuming any current flow. So for example, remember that the diode, that line on this side, is always the negative side of the diode. So the orientation of that would be the plus to minus. The voltage on this, with ignoring the resistors, is a minus 10.7. And on this side, you're not quite sure because you have V0, which is also tied to a plus 10.7. So we're going to kind of look at an approximation of being 10.7, which looks like the orientation would be backwards for D1, so we would assume that it is off. The orientation for this one, if this side is about 10.7 and this side is about a minus 2, has the orientation being the correct polarities, so we would assume that D2 was on. This is a rough way of getting just an estimate of which ones to make for the assumption. Again, we're going to analyze the circuit and then recheck that our assumptions were actually correct. So We did off for D1 and on for D2. So now we're going to replace them for the correct models. For an off, we are going to open it up, and then we have to remember we have to check that VD, and so we are going to have the polarity still in the same direction, so that VD for 1 has to be between here and here. For the diode 2, we're going to replace it with the same polarity as it was oriented. So that was a plus to minus, and we're going to replace it with that VDO value, which is 0.7 in this case. So this is now our circuit, and we're going to analyze this to find ID1, ID2, and the voltage V0, and then check the voltage VD1 to make sure our assumptions are correct. So now to analyze this, we can use node voltage. V0 is our node voltage. This is a hanging wire, so there's no current flow here. And so we just have VO minus 10.7 over 1K plus VO minus 0.7 minus a minus 2 over 1K equals 0. And we can solve for our VO. So we combine all the VO terms and take over to the other side. So that would be a minus. Minus becomes a plus. So that becomes a minus. And then I multiply that by 1K over 2. And so I get my VO value, which ends up being a 4.7 volts. And from there I can see this also has got to be 0 because it's open. So ID1 is 0, and then ID2 is going to be V0 minus 0.7 plus 2 over 1K, and then I plug in the 4.7, and I get 6 milliamps for ID2. So now that I have these values, I need to check that my assumption was correct. So for an on one, you're going to check that ID is greater than 0, and for off, you're going to check that VD is less than or equal to 0. So all we have to do is look at ID1 or ID2, and it is greater than 0. It's 6 milliamps. And then for VD1, I have on the plus side, I have a minus 10.7. So VD1 is equal to a minus 10.7, and then with no current there, the value on the negative side is V0. So I have a minus 10.7 minus 4.7, and I have to check that that is indeed less than 0. So minus 15.4 is less than or equal to 0, so therefore it is off. And those are my assumptions, which are correct. And so this solves the DC. Solve for the AC. So this is the question: if there's noise on that 2-volt supply of sine omega t, then what is the total value for ID2? So ID2 total will be your DC plus your AC. So we're going to replace this circuit with the AC model. And so instead of the the voltage source, we are going to remove all the voltage sources. So this DC value becomes a ground, and this DC value also becomes a ground. So the minus 10.7 also becomes ground. So this is because DC goes to 0. We're going to replace the 2 volt. It will be oriented the same way, but now we have a sine omega t as the value there. And here we're going to replace this with that small RD2. So the model for the AC is to replace it with this just resistor. RD2 was NVT over the ID2 current, and so N was given as 2, VT was 25 milli, and we use the 6 milliamps for the value for ID2. So this gives you a value of 8.3 ohms. So we can do the same thing again and solve for the current ID2, or we can see that there's only one voltage source, and so ID2 for the AC is going to be just your sinusoid divided by all of the resistances in that branch. So the summation of all those. So 2000 and 8.3. And so this will be your AC value. So your total value is going to be the DC value plus this AC value. So we have 6 milli plus that minus sine omega t divided by 2008.3 amps. And that is our total solution to finding ID2. Thank you for watching.